Hello. So I'm going to speak about ZKP. So the idea of this presentation is to present things that are mainly in progress, things that we are looking at, that should be a part of the next versions of various protocols in 1 to 5 years, maybe, something like this. Okay? So I will introduce what are ZKP, don't worry. And then I will explain how it can be used, how it is used today quickly on privacy, but as well how it can be used for basically strange things. Basically, we're using them to solve problems where we are not expecting to use ZKP for this. And the most important part will be around scalability. Okay, so ZKP, zero knowledge proof. So it's something that is actually quite old. So there's Mikali. He will be in Malaga, and you should go at this conference. And Mikali basically invented and got the Turing Prize for this invention of zero knowledge systems, together with Goldwasser, both at MIT. And what is this mechanism? It's a proof that you know something without revealing what you know. Okay, that's the ZKP. So to explain the concept, looks like at this Where is Waldo game. You know, you've got this Waldo game like this. And I'm going to tell you that Waldo is somewhere, but maybe it's me who drew it, and maybe I'm lying. So I want to prove you that Waldo is somewhere, but I don't want to reveal you where he is, because you still have to play the game. So the way I'm going to do it, I'm going to do a small hole in a very big black card, and then I will move it somewhere in a way that this card is fully hidden, but you see Waldo in the middle. And if I do it, magic, it is there. Okay? So that's this concept. By doing this, I've been able to show you that I know where is Waldo, but Waldo exists, but you don't know anything about where is Waldo actually on the card. Okay? So let's apply something a little bit more computer science, just a little bit more. I like games, so I created as well a Sudoku, and I hope it's the same name in English, I'm not sure actually. And I'm going to tell you that there's a solution, but you're not going to believe me. I want to prove you that there's a solution. And the way I'm going to do this is by defining a ZKP. So that's how you define ZKP, actually. You're defining ZKP with public inputs. And here the public input is going to be the grid that I've just shown. Okay, that's the problem. There will be a private input. The private input will remain secret to you. But in the private input, I will put the Sudoku solved. Okay, that's the solution. So I know the solution, I put it there as a private input. And I'm going to put a set of statements, which are basically knowledge. The statements are going to show that it's a real solution. All the numbers are represented in all colors, in all rows, and all squares. And as well, you need to do the basic stuff, which is, maybe I'm not cheating, so it's a real solution, so all the numbers are between 0 and 9, and the private part and the public part are in line. Okay? And if I can do that with a ZKP, actually we're going to see multiple statements. There will be a scheme, which is a mathematical protocol. There will be a proof, the proof that I will generate. The circuit, which is all the statements that I mentioned. And a piece of software that is implementing the protocol with a prover, something that will generate the proof from the circuit, and a verifier, something that you will run to check that the proof is valid. Okay? So this is basically a ZKP. And when we do something like this, it means that you're going, in a way, to trust a little bit the ZKP scheme, which is basically these mathematical constructions described in a paper, peer verified and so on. There's a prover, so it's my problem. I will use a prover to generate the proof. There's a verifier, which is a piece of software, so we'll have to believe that this piece of software is a good implementation of the ZKP scheme. This circuit, so we'll have to check this circuit, because maybe I'm telling you that I've got this statement, but what I actually implemented is something different. So this circuit is going to be quite important, and you will have to verify it clearly. And once we're OK with this, I can generate the proof with a prover, and you can verify this proof with a verifier. OK? It's simple. And the question is, what can you do with this? Except Sudoku. So the funny thing about this is basically when it was defined 40 years ago, it was just a mathematical tool without any interest. So just very few people were working on it. And that was it. And we basically recently discovered, I would say for 5 years now, we're discovering usages of these kind of things. And the very important points to remember here is when everything goes well, the idea of this system is that doing the verification is less expensive than redoing the work. Okay, so a mathematical guy working with me was saying, oh yes, it's really great, because I can check a mathematical proof without reading the mathematical proof. Okay, so that's the idea. The second point as well is it's a non-interactive thing, which means that I can send you the proof, and I can go away. You can check the proof alone without speaking to me anymore. Okay, which is quite interesting in computer science, because it means I'm just throwing it away and it's done. I don't need to be up for many times. So in real life, so something that has been used, for example, in Zcash, but as well in a new protocol on top of Ethereum, is to do private things. Okay, so this idea is that the private part is a secret, the public part is known, and the circuit is known, but the private part will remain a secret. So what you can do, for example, and there's a lot of variations around this kind of schemes, is you're going to say that you will have nodes, the amount will be a secret, and you will exchange nodes, but without revealing what's the amount of a node. So in Aztec, what they do is you've got a set of nodes, you're destroying them, but in the private part of the protocol, in the private inputs, you have what was the value before and what was the value after. And you're just going to have as a statement that you're not creating money. And the blockchain is just going to check the proof. So it doesn't care about the owner, it's just going to check that you're not creating any money in the transfer. Okay? Zcash is more or less the same logic. Interestingly, to remember when you speak about privacy, what we're hiding with just this subset of a protocol is how much you transferred. We're not hiding that you had a transaction between two people. We're hiding how much was transferred. And maybe what was transferred is actually zero. So we can play a little bit with this. If you look at Zcash, it's a little bit more expensive to do that, and I will come back a lot on the schemes and issues with this. And for this reason, you can see that there's around 50% of the transaction in Zcash that are actually protected, because you need to generate the proof, check the proof, and it's more expensive. Okay, so I will come back to this point. I was mentioning as well that you can do anything. So this one is interesting. And the problem that we are having at a point was something actually defined by Michael again. Michael is there. Was cryptographic sortition. So cryptographic sortition was proposed by Michael in Algorand, saying, I want to select openly a set of people. They will know that they will have been selected, but no one else will know until they reveal themselves. Okay? Well, the problem that he wants to solve is actually a cybersecurity issue. He says if you know that someone is going to do something in advance, you can attack him, you can do a DOS, you can do many things. So let's stay done until the work is done, and then you can push the result. It's too late to attack him, it's already pushed. Okay, that's the idea of a problem that he wants to solve. And he proposed a solution to this, and he didn't use the ZKP. He used something which is probabilistic, which has a side effect. To work, you need to have a lot of participants. And many people, like actually Filecoin, Ethereum, wants to use it with just a few participants because the task to do is expensive. And we actually found a solution with a ZKP. And interestingly, when we found it, it was quite expensive in our opinion, so it was 2 seconds. And we thought, okay, we should use standard cryptography instead of ZKP. It's going to be too expensive, so we put it away, we communicated it, and we said, okay, now we're going to look for something different. And actually, Justin Drake from the Ethereum Foundation looked at it and improved it by a factor 20 and make it practical. And the lesson that we learned is you can actually have, I would say, practical ZKP for small use cases. And here, you're basically on something that will take 100 milliseconds to generate. So something reasonable in many, many protocols. We're still on interesting things as well, so it's not something that critical. The fact that no one knows that you've been selected, it's not that important if it is in the protocol or not. So it's interesting because it means that you can use newer cryptographic schemes. You don't have billion at stake. It's a nice feature, but it's not essential. Still, from a protocol point of view, it means that you need to agree on the scheme that you're going to use, and we will see that there are many, many schemes. So the fact that you have a solution that today, a protocol that works, doesn't mean that you have an implementation shared between all the clients of a blockchain in production. That's likely to take a few years. But it's a second use case. And now the one that a lot of people are excited about it is to using around scalability. A totally different one, bigger. So, you know, in blockchain, you should not trust anyone, you should verify, okay? So at a point, I had mugs, I had 20 different things on this page with don't trust, verify, don't trust, verify, don't trust, verify. But what does it mean, actually? When you don't trust, it means that you have, in blockchains, to re-execute the transactions, okay? You don't trust the miner, so the miner is going to send you a block, and the block will contain transactions, and you're going to re-execute the transactions that are in this block to check that the miner is not lying to you. And in order to do that as a simple node, it means that you need to execute all these transactions, and it means that you need to have a state for all these transactions. So if you have 1 billion users on your blockchain, it means that a node needs to be able to store the data for 1 billion users. If you have 10 billion users, 10 billion users data. Okay, and it's a key bottleneck in blockchains today, because when you have more transactions, more users, your nodes need to grow, and they will have a lot of computer science issues like database cache misses and so on and so on. Okay, and that's, for example for Ethereum clients, the size of a state in the last versions. But here, again, we're executing the transaction to check that the miner is not lying. But with ZKP, we know that we can verify the proof without executing it. So that's the main point, okay? You won't execute, so you won't have a state. You will just check the proof that the miner has done a proper job. And this is called rollup. And interestingly, in this solution, there's no privacy at all, okay? While zero knowledge, you tend to think, okay, oh, zero knowledge means privacy. You can use zero knowledge, especially proof of executions, without any privacy at the end of the day. It's something different. So what we call layer 2 is something that is using a blockchain without changing the protocol. So a rollup is something that is built on top of a blockchain that will do a lot of things that blockchains do, but without changing it. So we will have proof verified by the blockchain, And the executed transactions will be on the blockchain, but they won't have to be re-executed by the blockchain. The proof is enough. So here are the main components. So we've got a user, and this user is going to send transactions. But instead of sending transactions to the blockchain, he's going to send them to an operator, a piece of software. And this software is going to manage the accounts for this user, and is going to generate a proof that he has done a proper job as working on the accounts. Okay? So this proper job, what is it? It means that an operator should check the signature of the user. The user is going to, as usual, signing transactions. So the operator is going to check that the transaction is actually signed by the user. The operator is going to check how much there is on this user account, and is going to prove that he has done this check. And the operator is going to decrease the account by what was transferred and to move it somewhere else, and the operator is going to prove that he has done this check. Okay, so it's checking for the signature, for the previous amount, for the new amount on the from account, and for the new amount on the destination account. And what will be sent on the blockchain is the proof that the job was done correctly. So as on the blockchain, you just have the proof that it's done. You don't have to execute anything. You know that someone has done it already. So it's a little bit more complicated in real life, and it will get more and more complicated in the next slide, because you can have multiple operators, because if you add a single operator, the operator could refuse transactions and say, oh, I don't like this user, I'm not going to do the transfer for him. He cannot change the account, but he can refuse transactions. But as you have multiple operators, you can, if someone tries to censor you, a little bit like miners today, you can go to another operator. And if we take the last version of Ethereum, Istanbul, we can go around to 1,000 transactions per second, compared to the 15 transactions per second that we can do today. And there's a world, because we need to understand a little bit more the magic here. So there's a few magic, which is here, while Ethereum, for example, can do whatever kind of operation. A smart contract, you can implement what you want in a smart contract. Be careful with security, but you can implement what you want. Here we're just doing transfers. And it's not by accident, it's because doing the verification is expensive, so it's a very specialized kind of circuit for just transfer operations. As well, we don't even support many accounts, because the more accounts, the bigger the numbers. The bigger the numbers, the more complicated the proof and the more expensive the proof is. Okay, so when we're opening, we're still on something a little bit specialized. And at the end of the day, it's Merkle trees as usual, but we don't care that much. So we've got a very simple transaction. And with this system, it has been implemented. And they reach, at this point, it was on the previous version of Ethereum 1, 500 transactions per second. But the small detail is there. When they generate the proof, it takes 20 minutes to generate the proof for 1,600 transactions. Okay? And if you push it a little, so okay, so you're telling me that I can do 500 transactions per second, but it takes you 20 minutes to generate the proof for 1,600 transactions. And you multiply things at the right point, and you say, oh, then if I've got a computer with 27,000 cores, which is basically Amazon grade numbers of nodes, it will work. And if I want to do 1,000, as I was mentioning, then I need this. And I'm skipping the memory because it's actually another kind of problem. But here it's exploding already. It doesn't mean that it's it's completely lost. It's not a lost cause at all, but it's adding a few complexity that are actually in progress. So, I mentioned the schemes. So there are many, many schemes. So the scheme is, it's a zero-knowledge system, but there are multiple ways of doing zero-knowledge systems, zero-knowledge proof. And there's basically one nearly every week. There's full explosions of a number of proposals. Because when it's written 2019, it's basically last quarter. With a lot of different subtleties that are there. That's the different properties that you have. So you're looking at the time you're going to need to generate the proof. Different schemes will be faster or slower. Okay? You're going to look at the size of the proof. Okay? When you're on a public blockchain, for example, you want the size of the proof to be very small. If it's a private deployment, you don't care that much. So it's another property that you will look at. You're going to look at the time it takes to check the proof. Time can be constant, can be linear, can be whatever. You're going to look at cryptography, is it quantum resistant or not? So basically it's going to last 20 years or not. And you're going to look at the setup, because it relies on randomness that is supposed to be pre-generated. And if you can break the randomness, you break the system. So that's a sample of these ceremonies about, look, I generated random numbers and no one can know what I generated because I'm destroying the computers that I used. Which is quite fun. It happens for Zcash. It is happening right now for Aztec. And you're looking as well cryptography, what are the assumptions used, and there are many of them. Okay, so that's all the schemes that we have. And at this point, none of the schemes are absolutely perfect. So the one that is used today, for example, in Ethereum, is this one, called the Groth 16. Because it has this constant time for the verifier, and the fact that the proof size is constant as well. But there are other schemes that are really interesting. Stark is great because it's quantum secure. You don't have any setups. You don't have to burn computers when you want to create something. But the size of the proof, so it's growing a lot, so you don't like it that much. At this point, all the schemes, there's new schemes coming, and there's likely a few years before everybody, before actually someone finds the scheme that is solving everything, and before everybody agrees on it. Still, something to remember is that it's still practical. I mean, this is used by Zcash and Ethereum. This one is really new, so a lot of people are interested. Plonk was actually produced by Aztec. So very likely for the next years, we will have a few schemes depending on what you want to do. This is great for public blockchains. This is great for private blockchains if you like quantum resistance. This is likely great for public blockchains as well if you don't want the setup and so on. So we're going to see this. We're going to see other things as well, which is when you have a problem, you can throw hardware at it, and that's what people are doing right now. So we've got the CPUs with 15,000 cores. So we hope that the new schemes will be better implemented, and maybe it will be just 10,000 cores. There's a multiplier. GPUs, so you know that already, a kind of specialized hardware for graphical environment by default, but as well for mining and for many things. And here we are approaching the end games, FPGA. So FPGA is really what everybody is looking at right now, because you can expect something like 100 or 1,000 improvements between the two. That's what people are expecting. And it's a kind of hardware circuit that you can configure. Okay, so here it's something very generic. A little bit less generic. Here it's hardware that you can configure yourself. And then it's totally specific, something that you build and you need basically 10 million when you're there. So FPGA, it's seen today as, okay, what we can do. So it means implementing a prover as a specialized circuit that you can find on Amazon for $2 per hour, if you need to. Which means as well a lot of implications in terms of security, because the prover is actually quite interesting. So if someone can generate proof that leaks and so on, it will be an issue. So that's where we are. And there are other use cases as well. I mentioned account management for rollups, but you can consider account management as a small part or something bigger. So the idea when you go there is to say, oh, we can actually have multiple applications that will agree on the account management, but they will then do whatever they want. Okay, so we can imagine, we can guess that we have here account management plus, for example, a gaming application. We can have here account management plus a decentralized exchange, and we can have here, for example, account management plus anonymous transactions between the members of this system. And then we just have to agree on how to transfer money between themselves. Okay? So here it's something that doesn't, rollups are implemented already in a proof of concept. Here we do have transfers. We know how to do them, but it's implemented as a proof of concept as well. And we don't have any other application than simple account management. It will take likely 1 year before getting there. And I think, yeah, no, I forgot that. Something that is getting considered as well is to use this kind of system as a way to manage what is called in Ethereum to cross-shard operations. So you can imagine as a way to manage operations between blockchains. Okay, if I simplify a little bit, a shard is a kind of blockchain. It's a huge simplification. It's wrong from many points of view, including security. But if I just want to simplify, you can see it like this. And what is difficult is to do transactions between those blockchains. And we're looking at how to use them in this context. Conclusions. It creates a lot of options to have distributed systems, basically because you can move a state out of the equation. It's used in production, so if you think that it's broken, this cryptography and so on, there's some money to make on Zcash. Don't hesitate. We think that it's going to be embedded in other protocols, like just small components for not critical features. But we see it as well as possibly used for critical features, like the capacity to manage thousands of transactions per second. With this small caveat, which is, okay, there's some work to do. Come back next year, likely. And that's it.
I know there should be a lot of questions. This is quite cutting edge. So questions? Okay, maybe I will start. So you were saying jokingly, okay, come back next year and you will see what is happening. But more realistically speaking, you were mentioning rollups before. When can we expect to see rollups really being part of solutions? Are we talking, and I know that you can't give a specific answer, but maybe in terms of scales, are we talking about months? Are we talking about years? Are we talking about decades?
So for the simple version of rollups, there are multiple teams working on it, and one team wants to have it in production on Ethereum basically for the end of the year. However, they won't reach those 1,000 transactions per second because it's just too expensive. They will have something much smaller, but they will have the whole scheme of multiple operators generating proof, the blockchain verifying proof. This will be in production. Their target, it's not us, they want to be in production for the end of the year. The Matter Labs that I mentioned as the guy who implemented these solutions a few months ago, they have something that is not very far from production as well. So the simple, something that works without achieving the full number is going to be in production soon. If we want to achieve 1,000 transactions per second, that's here at this point that we need to wait a little. it's going to be years, except if we really want to accelerate. The time, for example, this ASIC on paper, it works. I mean, you just have to push it. Just that the price is around 10 million. So people are going to wait a little before putting 10 million on this. And if you want to play slow, it will be likely 2 or 3 years around this way, which is optimistic but reasonable. FPGA, there's a lot of work on it. If people say, okay, we really want it, it's likely it can be put in production in a year around this. All the new schemes, I will say the ultimate stuff that we don't even speak about it, it's not recharge, is going likely to be 5 to 10 years. So Dan Bonnet, which is a well-known cryptographer in Stanford, has a few students working on this, and he basically says it's going to take 5 years. So the next PhD is going to be useless, but the PhD after the PhD will be okay. So 5 years to have a full mathematical solutions that you don't need to discuss anymore on it. That's what he says. I don't have any strong opinion on that. And then likely you need 2 years, 2 to 4 years to get it fully implemented, especially in Norway. So in 10 years it's a solved problem. And in 1 year it can be used.
Okay, very clear. Are there questions from the audience on this presentation? All right, excellent. Thank you very much then.